Hello and welcome to the first lecture on projectile motion. Projectile motion is unique because it is not linear. It is curved motion. And it's curved motion because the horizontal and the vertical velocities are independent of one another. The horizontal velocity remains constant. The vertical velocity increases and decreasing depending upon whether or not g is positive or negative. We will explore the uniqueness of projectile motion and solve problems relative to the principles of projectile motion. The first is that the horizontal component of motion for a projectile is just like the horizontal motion of a ball rolling freely along a level surface without friction. Vertical component is the component of a projectile's velocity is like the motion for a freely falling object. So we're going to put the two together. You can see that if something is free falling, its velocity is increasing as time progresses according to g. If a ball is thrown in the air upwards, it's going to decrease its velocity according to g. Here is a little experiment that you can run independently. And that is place a coin on the edge of a table so that it hangs over slightly, just before it would tip over. Place another coin on the table the same distance from the first coin, some distance from the first coin. Slide the second coin so it hits the first one, and both coins fall to the floor below. Does your answer depend on the speed of the coin? Explain. Let's look about something else. Let's say I have a rifle and I shoot a projectile, the bullet, horizontally towards the horizon, horizontal with the ground. And I then, at the same time that I pull the trigger, I drop a penny towards the ground. Will the speed of the horizontal motion keep the bullet from falling as quickly or more or less quickly than the penny or whatever piece of metal that's dropped at the same time the trigger is pulled? Here are the three linear motion equations that you should be familiar with at this point. And those are very simple. It's going to be d equals v naught t plus 1/2 gt squared, where g is gravity, and then vf equals v naught plus gt, and vf squared equals v naught squared plus 2ad. Here are the first 5 equations in our search for answers to projectile motion. Please write these down, memorize them, do whatever you have to do. You'll also be able to use your equation sheets in order to, when you take a quiz or test. However, it's very helpful if you know these equations and you become very intimately involved with them. So there are some of these equations that are simplifications of the 3 equations 2 slides ago, and we will be using some of those simplifications as we proceed with our analysis of projectile motion problems. For instance, look at number 7, ty equals vy over g. That's certainly a simplification of one of the 3 equations. Here are equations 11, 12, 13, and 14. Notice equations 13 and 14. In type 1, tx and ty are equal. In type 2, tx and ty are not equal. Tx is twice ty. So let's take a break for a moment. Make sure that when you're looking at this video, keep those equations separate for yourself to look at while you're doing the problems on this video. The problems on the videos are going to be very repetitious. We're going to do three types of projectile motion, type 1, 2, and 3. We're going to start with type 1. So keep those equations written down and separate from the film so that you can refer back and forth to them as we go from slide to slide on this tutorial video on as a lecture for projectile motion. This slide shows what happens with type 1 projectile motion, and that is the object is fired horizontally, creating Vx. It has a certain initial velocity in the horizontal motion. It falls a height dy in X number of seconds, going across the slide. And the time it takes to fall times the velocity is going to equal the distance it goes horizontally. So the ball will hit dx away from the cliff. At the same time, the ball would drop the distance dy. So that's basically it. So you have three major equations. You have Vx equals dx over tx, dy equals 5t squared, 5ty squared, and dx equals tx vx. And you can rearrange the vertical equation dy by t y equals root dy over 5. Here is the idea of projectile motion, type 2 projectile motion, where, remember the rocket problems, it's very symmetrical. As the cannonball flies up, it will reach the top in 5 seconds, and then it will reach the bottom in 5 seconds. It starts off 50 meters per second. It will fall at 60 meters per second. Now, the next slide will show you that the Vy changes. You can see that it decreases going up so that it becomes 0 at the d max, dy max, and then starts to increase again so that it is the same size when it's coming back down, and that the horizontal velocity at each frame, at each position the ball is in, is held constant. So both velocities act independently of one another, but together they create this parabolic shape. Here's another example where you see that the horizontal remains constant and the vertical is controlled by gravity, or G. So when you are doing a type 2 projectile motion problem, you have to determine what the components are. You're given the V naught, which is the vector at an angle. And so you're given the vector and the angle, and then you can find the x and y components and treat them individually. For instance, if I have the angle and the V naught, I can use V naught times cosine angle, cosine theta, will equal the Vx velocity. And sine, V naught sine theta will equal the Vy value, the vertical velocity. So now we have both legs. We have the vertical and the horizontal velocities. Now, always remember, we're talking about ideal paths, especially when we're beginning this. If you want to talk about the effects of air friction, then that's going to be a higher level physics course. But just to understand that, yes, there's an actual path and an ideal path. If you know how the ideal path works, then you can make the necessary modifications to come up with the actual path. But the main idea is that you have to learn the ideal path first, and then you can make modifications of the path based on air friction, etc. So here's a type 2 projectile motion problem, and we have the initial velocity v naught, and we have an angle, and the projectile is shot at that angle, and we can calculate the Vy and the Vx. V naught cosine theta is Vx, and V naught sine theta is Vy, and then from there we can apply several equations to resolve the height the projectile travels and the horizontal distance the projectile travels. Now, so here's the first two. We have V naught, we have Vx and Vy, and understand this, that if I was going to apply the equation Vy equals V naught GT, where V final is 0, I'm going to be able to simplify that equation as you will see. Okay, so these are the equations to determine Vx and Vy, where Vy is V naught sine theta, Vx equals V naught cosine theta, and these equations can be found on your equation sheet, and I would do myself a favor and simply memorize them. Now, here are some additional equations. Let's say you're not given V naught, where you can get Vx and Vy. Instead, however, you have Vy equals GTY, and if you need to come up with V naught, you have root Vx squared plus Vy squared, and then Vx you have dx over tx. You can find Ty is Vy over G if you have Vy based on V naught sine theta, and then theta equals arctangent Vy over x. And also don't forget that the Tx is twice Ty. Tx is twice Ty, and that's coming up clearly here. You not only have if you're given dy directly, you can calculate ty and then vy, etc. You also have dy equals 5 ty squared, and you can find dx by vx tx. Here's the first problem, where you have 800 meters in dx and 4,000 meters in dy, and you have dy is 4,000, so we can find ty based on that distance, that vertical distance, as ty equals root dy over 5. Here is the dx is going to be the horizontal, that's 800 meters. So now we can find ty. And then the question would be, what do you do with ty after you find it? So here's ty, 28.3 seconds. Now you have ty. Now remember, we're kind of working backwards here. Ty equals 28.3 seconds. What is going to be the next step? Well, the next step is going to find Vy. So Vy is the time times 10. Vy equals GTY, and that's 283 meters per second. So we have Vy. Now we have Tx, because Tx is twice Ty. So now the Tx is 56.6 seconds. Now we have Tx, and we know Dx. So Vx equals Dx over Tx, and Vx equals 14.1 meters per second. Now we have Vx and Vy. We can find V naught based on the Pythagorean theorem. We can also find the angle based on arctangent. So here's a summary of what we have after the first batch of calculations. Vy is 283 meters per second, and Vx is 14.1 meters per second. So in order to find the V naught, it's going to be V naught equals root Vy squared plus Vx squared, and that's going to be 283.4 meters per second is going to be V naught. And then the angle will be based on arctangent. The arctangent will be arctangent 283 over 14.1. Arctangent 283 over 14.1, which is 87. So you see that the V naught is very close to the Vy because you have a large angle. So the V naught would be close to Vx if you had a very, very small angle. So there you have the summary of what we've done so far. Now, the next we'll go to another problem, and we will apply the same logic in solving that problem. Be right back. Okay, the next problem is going to be dx is 40 meters and dy is 400 meters. Now, we sort of, in a way, have to work backwards to find what V naught is and the angle. Well, the first thing we want to do is we want to find Ty, which is 8.94 seconds. Vy, therefore, would be 89.4, and then we proceed from that point. Now, remember Tx, there's the 89.4. Remember Tx is going to be twice Ty. So if Ty is 8.94, then what is 2 times 8.94? And the answer is 17.88 seconds. So we now know what Ty, Tx, and Vy are. They are listed there. The Vy is listed. And what else do we have here? We have what Vx is 40 over 17.88. So Vx is 2.24 meters per second. So we're coming right along. Now, we have to find out what V naught is, and that's going to be root 89.4 plus 89.4 squared plus 2.24 squared, and that's 89.43, and that's going to be V naught. Now, the angle is going to be 88.6 degrees, because that's arctangent 89.4 divided by 2.24. Now, that's the answer. That's done. That's finished. Now, we're going to start another problem where we will, this is probably the last type 2 problem, where we have 1,000 meters per second at 60 degrees. So we're going to have to find the Vx and the Vy. There's the pathway or the trajectory, and Vx is 500 meters per second and Vy is 867 meters per second. And then the next thing we're going to have to do is find Ty, which obviously will be 86.7 seconds. That will be Ty. Tx will be twice that. And then we have to find, there's 87, we're rounding 86.7 to 87. Now we know what ty is, and we can find what dy is based on 5ty squared. And that will tell us what dy is. But first, let's find tx, which is twice ty, and that's 174 seconds because tx is twice ty. Now we want to find out what dy is, and dy is based on the equation 5ty squared, which is 37,845 meters, and that's the altitude, or dy max. Then we have dx is going to be 500 meters per second. Remember, the vx remains the same. Vx remains the same. 500 meters per second over 174 seconds is going to be listed there. Now we're going to start doing, in a moment, we're going to start doing type 3 projectile motion. But first, I just want to summarize what we did in this problem. Just let's summarize what we did, and then we'll start for type 3 electron configuration. Okay, be right back. Okay, before we go on to type 3, I want to take this opportunity to review what we just did. We were given V naught and the angle, 60 degrees. We found Vy and Vx. We took Vy and we found Ty. We took Ty and we found Tx. Now we have Ty and Tx, Vy and Vx. Now, I use the equation 5Ty squared, and that's going to be 37,845, and we took Tx, and we found 500 times 174, and that's going to be that's going to complete the problem. So the problem is really dx and dy. Dx is 87,000 meters, and dy is 37,845 meters. And now we will proceed to type 3 projectile motion. It is obvious that type 3 projectile motion is similar to both type 1 and type 2. But we're going to look at it really in terms of type 1 problems. Type 1a is ascending. Type 1b is descending. If you look at type 1 and you look where T1 is and you think the reverse, that certainly looks like a type 1. And the descending value, where the ball is going or the projectile is going from T1 to T2, is clearly type 1. Now, so you're given V naught, you calculate Vy, Vx, you calculate T1, then you can calculate dy2, you're given dy1, now you have dy total, and you can calculate T2. T1 times Vx is going to equal dx1, and Vx times T2 is going to equal dx2. And then it's all elementary from there. Then you can determine dx total. You have dy total, and that pretty much finishes the analysis for a type 3 motion. Now, just keep in mind that it is the T1, dy2, dy1, vx1, dx1, dx2, vx, and vy, and keep those quantities straight in your mind relative to your equation sheet, and this should be fairly simple to do. Now, you can also work backwards. You know, if you're given the times, you can work backwards. If you're given dy total, you can work backwards. T1 equals Vy over G, as we stated before. Dy2 is going to be 5t squared y. ty squared. And so the number one overriding problem with doing type 3 projectile motion is keeping all of the equations straight and when you use them. And that shall be done with a lot of practice. Now, this is a problem where a cannon is firing on a ship, and you see that the cannon is mounted on a platform high above the water and at an angle. So it will be type 3 projectile motion. The given information is going to be theta is 45 degrees, V naught is 10,000 meters per second, and dy1 is 2,000 meters. Now, be advised that this is not drawn to scale. This is not drawn to scale. Now, the Vy relative to that simple equation and Vx are listed as 866 and 500. That should be very easy to do. V naught sine theta and V naught cosine theta. And now we want to determine the time it takes for the cannon to reach D max, and that's going to be 86.6 seconds. 86.6 seconds to, now we can take that 86.6 seconds and determine the height in which it went above the cliff. The height in which it went above the cliff. So it would be 5ty squared. And there you have it. It would be V naught T1 cancels, so it's 1/2 GT1 squared. Don't forget that's called T1, and the answer is 37,498. You can see that this is not drawn to scale. It is not drawn to scale. So next, we know that dy1 is 2,000. So we're going to add that to it, and we're going to get 39,498 meters is the total distance from the D max all the way down to the water. All the way down to the water. Now, how much time is it going to take for it to go from 39,498 down to the water? And if it fell from rest, it would be 89 seconds total. So 89 seconds to go T2 time, and you know that it would be, we have the T1 time. We have the T1 time. So the T1 time is going to be 86.6 seconds times 500 meters. That'll be 43,300 meters. And then we take the T2 time, and we calculate how far it's going to go from the T1 boundary to the ship. From the T1 boundary to the ship. So you'll add to it 44,500 meters. So now the total distance, the total horizontal distance is going to be 87,750. 87,750 will be the total. Next, we're going to review all the equations we used to solve this problem. So to review what we did, I want to go back and look at a slide that we have already finished. And that is that you have V naught and the angle. Then you're going to find Vx and Vy. And then you're going to take Vy and find T1. After you find T1, you can find dy2, add that to dy1, and you get dy total. From there, you can calculate T2, and understanding that Vx remains constant, you can determine dx1 by using Vx and T1, and dx2 by using Vx, and T2, and you come up with a total dx total. Okay, so that's a review of the problem. Now let's do another problem. Let's say, and we're not going to use a picture this time, let's just do this by trying to remember visually what the picture is. We have V naught is 600 meters per second, the angle is 45 degrees, and dy1, or the cliff, is 1,000 meters tall. So then you calculate Vx and Vy first. You find that they are both 424 meters per second. 600 times cosine 45 is the same as 600 sine 45. Then from there, you want to determine the T1, which is going to be 42.4, dy2, plugging into the equation, 89 meters. Now you're going to add 1,000 to 89 meters, and then you're going to determine the time, and that'll be T2. You're going to determine the time. It goes from Dmax 9989 down to the ground 44.7 seconds. 44.7 seconds. Now, dx1 is going to be 424 times 42.4, and dx2 is going to be 424 times 44.7. Adding both of those values, you get the total dx. The total dx is 36,931. So follow 1, 2, 3, 4 when you're doing these problems, and you should not have an issue. The next equation, 25 meters per second on a hill 60 meters tall, dy1, and then theta is 30 degrees. Solving for Vx and Vy using V naught sine theta and V naught cosine theta, you get Vy is 21.7 and Vx is 12.5. Obviously, so we're going to put these in accordingly as vectors, component vectors. There we have it. 21.7 is the Vy and 12.5 is the Vx. Now, T1 is going to be 2.17. T1 is going to be 2.17. Now I'm going to plug 2.17 into the equation. dy equals V naught T minus 1/2 gt squared, because it's rising, so it's going to decrease 10 meters per second every second. And you get dy2 is 23.5. dy total, therefore, will be 83.5. Now, determining how long it takes from dy max down to the ground, you're going to plug that in, and you're going to find that dy max is going to be approximately 4.1 seconds based on the equation. T2 equals 2 times 83.5 divided by 10, all roots of that. And so now I have T1 and T2. I can find Vx1, which is going to be 12.5 times 217. That's 43,300 meters. And then 12.5 times 4.1 is going to be 51.25. Therefore, or 51.3, I think I'm going to call it. So then you add dx1 and dx2, and you get 78.4 meters as dx total. And that concludes the problem. One more problem to go. Good luck, and let's begin. Okay, this is the last one. Each slide is going to be 3 seconds after this first one. Make sure you stop this to try to do it yourself and see if you can come up with each answer before I present the answers. Good luck and goodbye. Okay, and that completes the lecture, and I'll make sure that lecture 2 is on very soon. Have a great day. Now, if you if you take notes on any of my lectures and you present those notes to me, I will give you extra credit. So it's going to be good for you to take notes on these lectures because they can be included in your chapter notes and you can use those on your tests. So there's no reason not to watch these lectures and to take notes on the lecture. Present me with the notes and I will give you extra credit, and then you can use those notes on your tests. Have a great day and enjoy, and goodbye.